Now we are going to learn about surface and upper level chart. So this is the diagram. The top diagram A shows four cities A, B, C, and D at different elevation above the sea level, all with different station pressure. So pressures are difference. The middle diagram B, if you look at, the represents sea level pressure of four cities plotted on a sea level chart. The bottom diagram C shows the sea level pressure readings of the four cities. In addition, the other sea level pressure reading at the location that is not shown in A and B. So isobar are drawn on the chart. If you look at the gray lines, is at interval of 4 millibar. So near the surface, atmospheric pressure decrease on the average by 10 millibars for every 100 meters of increasing in elevation. So about 1 inches of mercury for each 1000 feet rise. So if you look at the picture A, that city A has a station pressure of 952 millibar. If you also look at that city A is 600 meters above the sea level. Adding 10 millibars per 100 meter to its station pressure yields a surface pressure of 1012 millibar if you are looking at picture B. After all, the station pressure are adjusted to the sea level. If you're looking at C, we are able to see horizontal variation in sea level pressure, something we are not able to see from the station pressure along if you are looking at picture A. So when more pressure data are added, as exactly in the picture C, the chart can be analyzed and pressure pattern visualized. So one thing's come up, isobar. We know the isobar means the line connecting point of equal pressure. So isobars are drawn at interval of 4 millibar with 1000 millibar being the base value. Note that the isobar do not pass through each point, but rather between many of them with the exact value that are interpolated from the data given on the chart. For example, if you follow the 1008 millibar line from the top of the chart southward and observe that there is no plotted pressure of 1008 millibar. So 1008 millibar isobar come closer to the station with a sea level pressure of 1008 millibar than it does to the station with the pressure of 1010 millibar. With its isobar, the bottom chart, if you look at that chart C, is now called the sea level pressure chart, or we can simply call it surface map. When its weather data are plotted on the map, it became the surface weather map. The isobars in this figure have been smoothed to eliminate the small scale Weigels produced by the data collected at high altitude station and at the station that might have a small observational error. Otherwise the isobar might be significantly distorted. So that's why these lines are smooth and the distortion has been removed. So the sea level pressure chart described so far, we call it that constant height chart, because this constant height chart represents the atmospheric process at atmospheric pressure actually at constant level. So this means that atmospheric pressure in the constant level that represented by any chart is called the constant height chart. So constant height chart. So in this case, sea level, the same types of chart could be drawn to show the horizontal variation in the pressure at any level of the atmosphere. So in the next slide, we will see a 300-meter the chart. So another types of chart more commonly used in studying the weather in the constant pressure chart, or we call it isobaric chart. So instead of showing pressure variation at a constant altitude, these charts are constructed to show height variation along the constant pressure, the isobaric surface. So constant pressure charts are convenient to use because the height variable they show are easier to deal with in the meteorological equation than the variable of the pressure. So given that the isobaric charts are routinely used by meteorologists, let's talk more about that. Imagine that the dot inside the air column in this figure represent tightly packed air molecules from the surface up to the troposphere. Assume that the air density is constant throughout the entire air layer and that all of the air molecules are squeezed into this layer. If we climbed halfway up the air column and stop, then we draw a sheet-like surface representing this level. We will have made a constant height surface. This altitude representing 5,600 meter in this picture is where we would under standard condition. So measuring a pressure of 500 millibar, supposing that, observe that everywhere along this surface shaded tan in the diagram there are an equal number of molecules above it and equal number of molecules below it. So this condition means that the level of constant height also represents the level of constant pressure. So at every point on this isobaric surface, the height is 5,600 meter above the sea level. The pressure is 500 millibar. Within this simplified air column, we could cut any number of horizontal slices, each one at the different altitude, and each slice would represent both an isobaric and constant height surface. So a contour map of any one of these surface would be blank, as there are no horizontal variation in the either pressure or altitude. So the map would look like this way. If the air temperature should change in any portion of the column, the air density and pressure would change along with that. If you look at this picture, that we have colder air to the north and warmer air to the south. To simplify this situation, we will assume that the atmospheric pressure at Earth's surface remain constant. So the total number of molecules in the column above of the region must remain constant. So in this figure, the area shaded gray at the top of the column represent a constant pressure. We call it isobaric surface pressure. So atmospheric pressure at all points along this surface is 500 millibar. Notice that in the warmer, less dense air above 500 millibar pressure is found at a higher elevation or a higher altitude than the average, while in the colder or more dense air it is observed at much little bit lower than the average level. So for this observation we can see that when the air aloft is warm, constant pressure surface are typically found at higher elevation than the normal, and when the air aloft is cold, the constant pressure surface are typically found at the lower elevation than the normal. So this variation in height of isobaric surface If you look at this picture, that's where the constant altitude lines intersect the 500 millibar pressure surface. So contour lines connecting points of equal elevation are drawn on the 500 millibar pressure map. Each contour line of this picture tells us that altitude above sea levels at which we can obtain a pressure reading of 500 millibar. In the warmer air to the south, the elevations are high, while the colder air to the north, the elevations are low. The contour lines are crowded together in the middle of the chart. So where the pressure surface dip rapidly due to the changing air temperature, and there is a little horizontal temperature change. There are also few contour lines. So although the contour lines are lines of the constant height, keep in mind that they illustrates pressure as same as the isobar. So in these contour lines of the low height represent a region of low pressure, and contour line of the high height represent a region of low pressure, a high pressure.